Let's code up the sync pulse generator for the HackCPU VGA interface. If you've not watched my intro video, probably be good to do that because I'm not going to go over any theory. I'm just going to get into building. The link to that video is in the comments. So let's define our inputs and our outputs for the sync pulse generator. This generator is going to generate the horizontal and the vertical sync signals for us. So first of all, we need a clock. And we need a horizontal sync. So we'll stick that over here. And we need a vertical sync. Okay, at its most basic, this is what we need, but I want to make this generic. So I want to feed, instead of hard coding the timing values for these two signals in here, I want to feed them in to this module to make this module more generic. So there's a few, it's actually three sets of parameters that I want to feed in here. Most basic parameter is we need the total count of pixels for both the horizontal and the vertical. And when I say total count, I mean active and inactive pixels. So let's just create a couple of, or a set of pins to capture that. So we want, let's just call it horizontal pixel. Put that here. Yeah, horizontal pixel and vertical pixel. So the horizontal pixel needs 10 bits because that'll go up to, what is it, 1024, which will cover, a horizontal resolution of at least 800 by 600, which is way bigger than we need. Vertical pixels, let's do 9. Again, that'll go up to 512, so should be plenty. Your mileage may vary. If you want something more, you certainly can do that. Okay, so we also then need, so this defines the total duration of the pulse, but we need the duration of when we are in active horizontal syncing or in active vertical syncing. So we need that that count as well. So let's just copy those and paste those. So let's call this one HPIC sync. And let's call this one VPIX sync. Let's put those below the counter variables. And we need, to make this totally generic, if you watch that video, you'll remember the intro video, you'll remember I talked about sync polarity. So each one of these so there are different standards that define the polarity of each one of these. We're going to be using the CVT standard. If you really wanted to make this generic, you would make it so that you could define the polarity. You could, have some flags that would tell this which polarity that you want. And that's what I want to do. It makes it a little more complicated, but I like to have this thing totally generic because I'm going to be using it myself for maybe other purposes, other videos, etc. So let's just define some pins, 2 more pins. And, we've got positive going or negative going. How do we want to name this? I think I'm just going to name this HSync pause, so that when HSync pause is true, that means we have a positive going horizontal sync. And then likewise a VSync pause. Something like that. Get all these lined up. Okay. So a final thing that I'm going to do, and I'm going to speed the video up, is just put tunnels on all these because it just makes it for an easier schematic drawing exercise. So cue the multi-speed. Okay, have that done. Now let's work on the horizontal sync first. So if we think about what we need at its most basic level, we need a counter that's going to count up to HPICs, and we need some comparator to make a determination as to when we get there. So let's do that. Counter sitting in here. Way too big. Okay. And we need a comparator. Oh, where's my comparator? Probably under arithmetic. There we go. Okay, so let's deal with our counter first. This bit is up, down, so let's always count up. This bit. Okay, so given that it's the horizontal counter, we never want to, we never want to load data. So we're never going to present this counter with a starting value. We always just want it to start at 0. So we're never going to load it. So let's just wire that to ground. And that is the value to load. Again, we're never going to load it. Enable. So this counter is going to free run. It's going to count all the time. So we just want the enable wired to positive because we just want it to run all the time. Positive voltage. The clock, obviously, we need one. So let's wire that up. And okay, so for the output, we want to compare our counter value to HPICs. And of course that needs to be 10. Oh yeah, and not 2's complement because these are going to be unsigned numbers. And this one also needs to be 10. Right, so at the point that these become equal, then we actually want this counter to reset itself. And the Logisim counter module has the ability to do that with a maximum value. And then you can wrap around, which it's cool, but I don't like it because it makes it so that you can't genericize. So we've got this HPICS value. This is the value that would ultimately go in here. But I can't. It'd be nice if there was another input hanging off of this thing where I could just wire this to the input, but you can't do that. So what we're going to do is when these two become equal, then we want the counter to be cleared, which means that the value will start over at 0. So this defines the total duration, duration of the pulse, but we want to know when it's time for a state change to occur in the pulse. So so when we're in active horizontal syncing, so we just, we know what that duration needs to be because it's in HPICS sync. So we need another comparator to compare based on the output of this one, when we've tripped this value here. So let's put another comparator here. Again, when stick it here, I guess it's still probably not the right way. And and our comparator needs to be 10 bits. Again, not 2's complement, but unsigned. And then we're comparing that against HPICS sync. Okay, so let's think about this. When our counter is less than HPIC sync, that means we are in the, active horizontal syncing part of the pulse. So we could simply just do this. And for a positive going horizontal sync, we'd be done. But remember, I had this bit here that is trying to define whether we want a positive going horizontal sync pulse or not. And so it's, of course, not quite that simple. There's several ways to do this probably. My programmer brain tells me to just put a mux in here, muxing on this bit value, and either invert this signal or not. Let's just do that. Let's throw a mux in there. Our polarity signal will be the selector. So an horizontal sync positive is 0. That means we want a negative going horizontal sync, which means on this input right here, we want to negate what's coming out of our comparator. So let's put in our inverter. But then if this is positive, if H sync is a 1, then that means we want a positive going signal, which is the default coming out of the comparator in the first place. So we want that. And then the output of our mux is what horizontal sync is. So the VSync is very conceptually similar to this. So we need, again, a counter. I could copy and paste, but I think it's better to do it step by step again, even though they're very similar. So let's add a counter. So we'll always count up. And again, we're not going to load data from input. So we'll wire this to ground. It'll always start at 0, and we'll clear it as such. And again, we're never going to present data to it. Okay, so now in this case, enable will not always be wired positive, because once we, this is going to count the number of lines, the number of, vertical lines. Once we get to the end of this counter here, get to the end, the total end of the line, then that's when we want to increment. So we want this enabled at the point that happens, and that happens when the HPICs and the counter value are equal. So what we want then is a wire wired up like that. Right? Enable this counter when this equality occurs. Let's put our comparator in to deal with the entire number of lines, kind of similar to what we did up here. Let's see, where is it? Comparator, here it is. So again, we want to compare a line counter to VPICs. And yeah, this needs to be 9 bits. And again, unsigned, because these are all positive numbers. And this, of course, needs to be 9 bits as well. So same deal here as here. Once we get to an equality, so once the counter gets to the number of vertical pixels, that means we're done, because again, it's zero based. So if this is 480, as in 640 by 480, and we get to 480, then we want to clear this counter back to zero. So as in above, we want that. So this takes care of the total number of lines, but we want to know when it's time to actively be in V-syncing, and that is defined by interrogating our counter against the VPix sync input. Again, conceptually similar to what we did up here for the horizontal. So we need another comparator. And we'll be comparing the output of our counter of course, this needs to be 9. And again, unsigned. And then we need to be comparing that against VPix sync. And I need to move this over a bit to give some more room. Still not quite enough. Okay. When we are less than, when our counter is less than VPix sync, that means we are in the active portion of vertical syncing. So again, we could simply do this and be done, except that we have this polarity indicator to determine whether we want positive or negative going vertical syncing. So just like above, I want to do that with a multiplexer. And again, our multiplexer will be driven by the vertical sync positive flag. When vertical sync positive is true, that means we want a positive going sync pulse, which is the default. When it's false, we want a negative going one, which means we want it inverted. So that means the 0 needs to be the inverted signal. So let's put an inverter in. And again, it's when the counter is less than our sync count, we want an inverted signal. On the other hand, when our sync positive pulse, or when our vertical sync positive flag is 1, that means we want a positive going pulse, which is the default. So we wire it up like that. And then finally, that becomes our vertical sync. All right, let's create ourselves a test harness. First, though, let's rename this to what this actually is. This is our sync pulse generator. And so we want now, let me close these up a bit. And so we want a test sync pulse generator. Sure. Let's wire this up with a clock. And, okay, sure. We'll put some pins in because it might be fun actually on our FPGA to flip the polarities on the fly, even though practically speaking, you would never do that. But it saves me having to resynthesize this. Okay, so I'm not going to do that here. I definitely don't want to set the state on the board. That would be annoying. So let's put in some constants to these inputs. Great. Now all we need are 2 output pins. Cool. And for the mappings, you will notice that I have the clock set to the far pin down here, and I have vertical sync on this third pin and horizontal sync on the second pin. And then these top 2 pins, I have the horizontal sync positive and vertical sync positive set here. So let's synthesize this. Okay, synthesis is done. Let's load our design. Let me switch over so you can see what's going on here. There's my, as you can see, here's the Digilent board. And I guess first let's hook up. I have the probe plugged into the spot with the clock. Let's make sure that we're getting the clock rate that we expect. So I'm going to hit program. And there's definitely something going on there. And there we go. We've got a 12 megahertz clock. Perfect. That's what we expect. So let's put it on the horizontal sync pin. And yeah, I have multiple probes, but I just haven't hooked them up. And I have our H-sync pause and V-sync pause connected up to the positive voltage. And so that should imply a positive going signal, which sort of, hints at what you're seeing over here on the scope. But let me change the scale here. And we see a positive going sync at 18.7 megahertz. So let me see if that is right. I believe that's right. Let's have a look. Have our calculator up. So we got 512, 256, a 12 megahertz pixel clock here. And so 640 by 275 and a 48 sync pulse and a 10 vertical sync pulse, which should yield a horizontal frequency of 18.75. And that's exactly what we're seeing. Cool. So let's switch this over. To our vertical sync. Okay, so this should be, somewhere around 70 hertz, give or take. So I need to turn this down for sure. Our period on the vertical should be, I'm looking at the calculator, should be about 14 milliseconds, you know, roughly 70 hertz, give or take. So for 14 milliseconds, so we should be seeing a pulse here, and we're not. It's just high. It's high all the time, and that is not right. So what could be the problem? So one of the things, so that's telling me that this is not counting, perhaps, because a high going pulse means, yeah, because we have this set to high. That means that we're in vertical sync, which means it's never leaving vertical sync, which means this is not counting to get up to this value. And remember, I was talking before about this asynchronous clearing, and you know what? It occurs to me, you know, this comparator is obviously not clocked, and so I'm wondering if we get to this condition being true, and given that this is an asynchronous reset here, is there not enough time elapsing such that there's time for this counter, which is counting only by the clock, to pick up on the fact that it should be enabled for a clock tick in order for it to count up by 1? I'm kind of suspecting that may be the problem here. So another way we could do this is, you know, I've noticed, or I had talked about setting the load to 0 all the time and not loading any data value in. But what we could do is we could set this signal, or route this signal over to the load pin, and then just load in a 0. And that would load in at the next clock. So this would occur at the next clock tick, which also would clock, or, you know, have this signal available long enough for the next clock tick if it was routed down here as well. So so let's try that. So we're going to put a constant in of 0, and we need 10 data bits. And so instead of going to the clear, instead what we want is we want this routed to this this load pin. So when it loads, it's going to load a 0, and then we're just going to leave the clear alone. We're not going to use it. Okay, I think that would work. I also think that the same, even though I don't think there's any dependencies down here, I think the same concept should apply here as well. Because doing things asynchronously when you're counting on synchronous operations are usually not a good idea. Okay, and we need this signal instead routed there, like so. Let's give it a shot. And there we go. Okay, we're done. Let's see what happens. I've hit the program button. Aha. So that's showing 68 hertz. And so vertical frequency 68.1182, which I guess I'm going to count that as close enough. I may run some simulations to see if it's doing exactly what we think, but this looks good. Let's switch it back, and let's move our signal back over to the horizontal. And that's showing 18.6, which should be 18.7. So I'm a little skeptical that it still might not quite be right. I think with a simulation with some test data, some small test data, we may be able to be much more certain that this is producing the exact right signal. But before that, so this is showing our positive going. So let's change our resistors. So I've moved those over to negative. And as you can see now, we have a negative going pulse on the horizontal sync at the same frequency. And also we have a negative going pulse on the vertical sync at the close to correct frequency. So I did realize after looking at this offline that since this is being clocked now, once we get to the end of the count, again being zero based, so if this is a 640 by 480, once we get to 639, then the next clock tick is when it should be cleared. And so what that means is once we get to equal, this is going to become high, and then the next clock tick is going to wind up clearing it. So what I'm going to do is I'm going to put some arithmetic in here because I don't want to have to remember when feeding into these parameters that they're zero based. I just want to be able to put in, say 640 by 480 or whatever. So I'm going to put some arithmetic in here to subtract 1 essentially, because I still need to use the equals here because it's going to be equal on one and only one trip around the clock. So I'm going to go ahead and just do that real quick. There we go. I think that'll work nicely. So I want to go back and run a simulation because I'm just not quite comfortable with how the vertical sync was working. It just didn't seem like it was quite within spec of what the calculator said. So what I decided to do is I went in here and just changed some of these values to smaller counters so we could simulate this a little easier. So I got a horizontal resolution of 10 and a vertical resolution of 5, and then I've got the sync pulse for horizontal at 3 and the vertical sync pulse at 2. So that should make a simulation fairly easy to look at. So let's run the simulation. And have a look here. We start here, we should see on the vertical sync. Well, let's look at the horizontal sync to make sure that that looks correct. Yeah, we should see 3 ticks. 1, 2, 3, and then 7. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 ticks. So a total of 10 for the horizontal sync. And then we should see a total of 5 with 2, a total of 5 horizontal syncs within the context of 1 vertical sync. And the vertical sync pulse should last 2 horizontal sync lines. Let's see, 1, 2. There's the 2. And then this should be 3, but it's not. And in fact, these waveforms, a horizontal sync and a vertical sync, should be happening together. When the vertical sync goes off, it should align with at least a horizontal sync row. So I'm already seeing something that just does not look right here. So it looks to me like this is happening a clock tick after. So after a little bit of work offline, I did manage to find the problem, so I'm going to show you. But just want to show you that the waveform now looks correct. So we have 2 horizontal sync signals followed by 3 horizontal sync signals here, and 2 on the vertical sync. Our parameter was 2, so there's our 2 horizontal sync signals. And then when the vertical sync is not active, there should be 3 horizontal sync signals, and there they are. And then remember, these were 1 clock signal out of phase. Now they are perfectly in phase with each other. So the waveform now looks correct to me. So let me show you 2 things I had to change to make this work right. So remember, I had subtracted 1 from the VPIX, but what I think is going on here is that this was not allowing the last complete waveform to finish, because of course you have to have all the horizontal picks done before you can reset this thing. So I'm going to remove this counter here. And so that gave us 3 horizontal lines when the vertical sync signal is not in the vertical sync state. And then the out of phase problem, this wire here was wired up to the load. However, once this is signaled, this gets incremented, this counter gets incremented, but it's not until the next clock cycle that it actually gets cleared. But once this increments and rolls over, we actually want this to immediately flip to 0, which would correspond to when the horizontal counter flips to 0. So those two changes now seem to make this work properly. So I'm going to go ahead and remove. And those were fairly tricky problems, and of course, the load. It's not going to be loading 0. It's just going to be clearing from this from this asynchronous clear signal, and this should probably always be ground, because we're never going to load that value anymore. So I'm going to go ahead and put a ground signal here. So if we're going to resynthesize it, we need to put our expected value, or our correct constants back in here. Those are original values. All right, let's go ahead and synthesize this again. Okay, it's finished. Let's load up the design. Let me flip over so we can take a peek. And we are getting a frequency of 68 hertz, which is much closer to the 68.1 on the calculator. Let me change it over to the horizontal sync. And that's coming in at 18.7, and this says 18.75. So that looks definitely correct with a period of 53.4 versus 53.33. So yeah, I would say this is now working. Thanks for watching.